If an airplane travels 60 degrees north of east for 104 kilometers, how far east and how far north did it travel? In other words, what are the magnitudes of the east component and north component of this plane's displacement? Okay, so the first thing we're going to want to know is the directions northwest, east, and south. What is their relationship to each other? So if we're looking from a bird's eye view of Earth, looking from the top down, then we would have this arrangement of north, west, east, and south. Let's go ahead and create a coordinate system for them. And let's assume that our displacement starts from the origin and it goes 104 kilometers north of east. So first, let's think about ourselves going east. And then let's go 60 degrees from that direction, right? So the east direction would be this direction. We want to go 60 degrees north of that direction. That's what north of east would mean. Let's label our displacement vector here. It's delta r because we are traveling, and the delta r's magnitude will be 104 kilometers. Okay, great. Now in the past, we had used components of vectors to find vectors. Now we're going to do the opposite. We're going to use a vector which is at an unusual angle, and we're going to find the components of that vector. Now doing this requires trigonometry. What we have to do is we want to first project our vector down to the x-axis, and let's also project our vector to the left so that it hits the y-axis. And we want to sketch the components of the vector. So if this is delta r, then this could be called delta rx, and this one would be delta ry. These are the components that we're trying to find values for now. Now there's a couple ways we can do this. You can do it by creating your own trig triangles and then solving those, as you may have in a trigonometry class in the past. Later in this video, I'll also give more advanced physics formulas that can find the components quickly, if you know the standard position angle of the vector, which we actually do in this problem. All right, so let's start it off with just your own trig triangle. How would that work? From your past, you may remember the acronym SOHCAHTOA. And what this tells us is a relationship between sine of an angle and the sides of a triangle. Sine is the opposite over the hypotenuse. Okay, so the S is for sine, O is for opposite, and H is for hypotenuse. We have another relationship, cosine theta equals the adjacent over the hypotenuse. So CAH. And then finally, the tangent of an angle will be the opposite over the adjacent. Those are the three trig relationships which you might use to find those components. Why? Because we have a right triangle here. And that's what you need in order to do SOHCAHTOA. All right, so just on the side, I'm going to write down what I have. I know that the theta is 60 degrees. I was also given this long edge of the triangle, which is the hypotenuse. So I know the hypotenuse is 104. I would like to find the adjacent side. That is the leg that is touching the angle. So which trig function would be best for us to use considering what we have and what we want? For this one, I'm going to use the cosine theta formula. So let's do cosine 60 equals the adjacent, which is going to be delta Rx, over the hypotenuse, which is 104 kilometers. Now we would solve by multiplying to the other side, revealing that delta Rx is actually the hypotenuse times the cosine 60. And that gives us 52 kilometers. So that is going to be the east component of the displacement. All right, next, we'd like to find delta Ry. Now, you can see that the left side of this rectangle is going to be the same size as the right side of the rectangle. With that in mind, we can label this leg of the triangle delta Ry. Now, which trig formula will allow us to find the opposite leg when we know an angle and the hypotenuse? That would be the sine formula. So let's do sine 60 equals the opposite, which is delta Ry, over the hypotenuse, 104. We'll multiply to the other side. And we get 90.1 kilometers. Let's write that in now. All right, so what other method can we use to find these? Well, there's a general formula that always works for any vector, as long as you know the standard position angle of the vector. Here's what it looks like. And I'm going to write it generally, which would mean it would work for any vector, not just a delta R vector. The formula says that for a y component, Vy equals V sine theta standard. V stands for the magnitude of the vector, so it's the length of it. And theta standard refers to the angle of the vector in standard position. Those are the only two things you need to know in order to find the vertical component of that vector. And then there's a formula for the x component as well. Vx equals V cosine theta standard. These formulas turn out to be really useful, but one thing you have to keep in mind is that if you're assembling your own triangles for these with SOHCAHTOA, then the theta you use does not necessarily have to be the standard position angle. In fact, it often shouldn't be. It should be a triangle of your creation. Here, though, if you want to always use sine with y and cosine with x, you have to have the standard position angle, and I'll do more examples of that in future videos. Now, as you can see here, if we do plug in, we're going to get the same answers that I had gotten above. The magnitude of the vector that we had drawn was 104. 104 sine 60 is actually right here. And over here, we'll have 104 cos 60. And we had gotten the same thing right here with SOHCAHTOA.